Hi everyone, welcome to this week's lecture, which is Multiple Linear Regression Part 2. And in some exciting news, the black bar that you usually see around the edges of these videos are gone. So learning every week, your learning of learning, turns out if you have it to capture your window versus your screen, the aspect ratio changes. And so screen capture is the way to go. So here we are, full white space around the screen. Hopefully you enjoy it, or maybe you don't. Maybe you have the nostalgic like VHS tapes. I mean, I don't know if that reference is is relevant or dated, but hopefully you like it, is the main summary. Let's get stuck into the second part of multiple linear regression. So the focus or overview today, we'll do a quick summary or review of what we did in the last lecture in multiple linear regressions. We're going to cover semi-partial correlations. We're going to talk about residual analyses, interactions, and analyses of change. This is really exciting because a lot of these terms you're going to read in papers that you're looking into, and you'll have a good sense as to what they mean, not only statistically, but conceptually. When do you ask the question as to whether you're interested in looking at an interaction term or not? And what does it really mean? How does it differ from our normal regression models that we've looked at so far, which have all been additive? We're adding the variables into the model. And so all shall be revealed. So sit tight and we'll find out together. I mean, no, I do know that's not accurate, but we will learn as we go. So the summary of multiple linear regression, there's sort of twofold. Is the purpose of multiple linear regression is to examine the linear relationships between two or more predictors, which are your independent variables, and a single outcome variable, which is your dependent variable. So conceptually, if you think of correlations, you should be thinking of the x-axis as your independent variable, your y-axis as your dependent variable. In multiple linear regression analyses, this logic still holds, but it's just that you have multiple independent variables, and so it becomes multi-dimensional. So don't worry about that. Really, the key takeaway is that you have these multiple independent predictors. And so what that means is you're saying, what is the association between X and Y after controlling for some other variables? For example, what is the association between my technical abilities with lecture recording equipment and student satisfaction after controlling for whatever other variables, if I've had coffee or not, or if I've gone for some exercise, or if the students are tired, all these other factors, right? So that's the models, because at the end of the day, you may be saying, well, does the quality of the lecture, is it associated with the, or enjoyment of the lecture, is it associated with the black bar around the screen, or does it, in fact, is that variance accounted for by whether students are interested in statistics or developing a love for statistics, or whether they are tired, or whether all other factors. And so it allows you to sort of ask questions in these ways. And then you want to develop a theoretical model. And so we looked at some Venn diagrams previously, and they're very simplistic, and we'll have some more today because I think conceptually they can be really useful to get a sense as to what's going on when we're talking about shared variance. And today we'll be talking a bit about unique variance. And then the path diagram, which is quite simply the pointing of variables in their directions. You have one variable and another variable, and the arrow between them, and sort of indicates that this variable is associated or maybe even more causally related to the other variable. And so conceptually, I use path diagrams quite a lot when thinking about research questions. I try to get a sense as to which variables are associated or impact the outcome variable of interest, and maybe even how the variables are related to one another, and getting a sense of shared variance. This is all theoretical. It's not something in itself that I'm putting into the statistical model, but it's helping me understand, well, is it important for me to control for this variable or not? Does that variable have likely have a relationship with my dependent variable or my independent variable, and then should I control for it? So it's really helpful in thinking about what variables to include in your model or not, and also getting a grasp of the literature in this sphere of factors that could be relevant in my multiple linear regression model? Which should I include? And so that's really, really useful. And you can express your model as one hypothesis per independent variable for when you're writing analyses or research questions. It's if for your basing it off your analyses, you have a hypothesis based off of what you expect to occur given the literature. So the summary was assumptions checking is always important, and that's what we have in multiple linear regression. We went through all of these assumptions, the level of measurements, ensuring some sample size guidelines, normality, linearity, homoscedasticity, multicollinearity, and that the residuals are normally distributed. And then we also talked about outliers, so including multivariate outliers, and it's important to check for these things because your results may differ as a consequence of outliers. And with all of these assumptions, these are really important to look through. And what you'll find when you're reading papers is not always do authors actually publish their assumptions. Actually, more often than not, it's quite rare to see. And in reality, I think that's because of journal limitations. Very long time ago, journals were published in paper format, and so they had to put word restrictions on those journals to ensure that they could fit important papers into each volume or issue. And so I think through that process, assumptions, people make the assumption that people are checking their assumptions when it comes to research. This isn't always published. So you may be reading papers and asking yourself, well, they're not actually reporting that they have met the assumptions of linearity in their models, or that they have no multicollinearity that's occurring, or if there is, they've addressed it transparently. But in some cases, you'll find that it's important to remind people, hey, have you met the assumptions of linearity? I actually had a colleague one time who was working through a problem and kept getting really unusual results and didn't know what was going on, why the results were occurring the way they were. And so in a discussion, a question was raised of, are those variables related to one another? Are they quite close to the independent variables closely related? And they checked multicollinearity, which should have been checked in the first place, but they checked after and realized actually, yes, there was a lot of multicollinearity, and that was causing some unstable estimates to occur, which was resulting in the confusion. And so especially it's very easy to, as you've seen already, conduct the analyses without checking these things, but hopefully these stories emphasize the importance of rigorously doing it with every analysis that you're doing. So check your assumptions, very, very important. Otherwise, things can go awry at the end. And also explaining why that's not always done in research, but there's a certain trust that researchers place that people should do it. But more and more now, it's getting to the stage where data is being made available openly to people. So as you do your research, if you can create your upload your data set, if you have the approval to do so, or if you can create a simulated data set based on the properties of your data, then others can use that and verify your results. And so therefore, they can check assumptions for you as well. So science is improving because reproducibility is really a critical thing. And it's good to have trust. We have to have trust with caution as well, particularly in science. And then we talked about choosing the type of multiple linear regression, including standard or direct, so it's simultaneous regression, hierarchical or sequential, and then stepwise, which is forward and backward, largely computer driven. So the standard one is what we're familiar with in terms of putting the variables into the model and seeing the outcome. The hierarchical or sequential was actually for a very specific type of question, which was, does this model account for additional variance above and beyond the original model, right? Or these set of variables, do they account for how much variance than the initial set of variables? So whilst at the end of a hierarchical regression model, model 2 or 3 might be the same as what you would do in a standard regression model, it's really also about the comparison between models to see, well, how much additional variance is accounted for. And then stepwise was using computer statistical tools to be able to say, well, what variable should go in or get removed. Excellent. And then we also talked about interpreting the output extensively, right? So in terms of what the big R meant in terms of the relationship between variables accounting for other variables, R squared, which was the variance account of shared variance between variables, and how much of the variance in the dependent variable is accounted for by the variables in your model. And then the adjusted R squared, which was about the population level. So R squared is about your sample, adjusted R squared is about your population level. And then we talk about the changes in R squared, so the hierarchical changes that we see, and across models when we're doing a hierarchical regression, and also the ANOVA test to see if the model that we have, if it's our first model explains the variance, it is a better fit of the data above and beyond the original model. And the baseline model is typically the mean of your dependent variable. Now, for each independent variable, you can standardize the coefficient, which has a lot of utility. You always are talking about the size, direction, and significance of effects. And you can standardize the coefficient to allow you to compare the size of the effects between different measures. Or you can have unstandardized coefficients, which is really useful for interpretability. And then semi-partial correlations, which is what we're going to do right now. So that's another component that you can think of as to representing our understanding of a variable and its contribution to a dependent variable. So what are semi-partial correlations? So before we get stuck into it, just imagine this Venn diagram. Well, you don't have to imagine it, it's right in front of you. So look at this Venn diagram, and you can see that there's two blue circles and a purple circle, right? So the blue circles are your two independent variables, your purple circle is your dependent variable. So you have your dependent variable and then two independent variables. And really, when we're talking about the shared variance, the R squared, the coefficient of determination, what we're really talking about is all of the overlap the independent variables have with the dependent variable. And so we're really talking about A, B, and C, right? If we add all of those up, A, B, and C, we get R squared. And that's the variance explained in the dependent variable by our independent variables. And so what is a semi-partial correlation? Well, if we just look at B here, so if we just look at the variance in the dependent variable accounted for by B, this is the unique relationship between independent variable A and dependent variable here after controlling for independent variable B. So this is the unique contribution of independent variable A on the dependent variable. So that's what B represents. So it's the unique variance accounted for after controlling for independent variable B. Why do I say that? Because if you remove independent variable B, you can see the unique variance becomes A and B, right? Because it's the only variable there. But when you put independent variable B in, you can see that actually there becomes a bit of shared variance, and then there's unique variance for B and unique variance for C. So again, the same logic, if you look at what C represents, that is the unique relationship between independent variable B and the dependent variable after controlling for A. So it's really this C section here, that's the amount of variance that is unique to independent variable B and the dependent variable. So it's the unique relationship between the two. So that's when we're talking about semi-partial correlations, the key thing to remember, it's about the unique correlation between the two, the unique relationship between the two variables. So when you're interpreting multiple linear regression coefficients, again, you want to draw a path diagram or a Venn diagram like this one. You want to compare the zero order, that's just your standard Pearson correlation, and semi-partial correlations for each independent variable to help understand the relationship amongst the independent variables and the dependent variable. So a semi-partial correlation will often be less than or equal to the correlation. So if a semi-partial correlation equals the correlation, then the independent variable predicts the dependent variable, right? And so I'll give you some examples of what this means in a second. So if the semi-partial correlation is less than the correlation, the independent variable's explanation of the dependent variable is shared with other independent variables. So here's an example, right? So you have your independent variable A and your dependent variable, if you just computed the correlation between these two, and you would get A and B, right? But if you just compute the semi-partial correlation, you just get B. So this is why I'm saying the semi-partial correlation is often at times less than what you would see in the correlation, but sometimes it can be equal to, right? And I'll give you an example when the variable is completely unique. So an independent variable may have a significant correlation with a dependent variable, but a non-significant semi-partial correlation. So what's going on here? So this indicates the unique variance explained by the independent variable in the target population could be 0. So the independent variable is not significant. The shared variance between these variables, the shared variance is actually what's accounting for this relationship. So you can compare the relative importance of predictors using beta, so standardized betas, and or the semi-partial correlations. So I think this diagram helps explain a lot of the concepts that we're looking at now with the ideas of semi-partial correlation. So in terms of semi-partial correlations, you can it can be used to get a semi-partial correlation squared coefficient, right? And this indicates the percentage of variance in the dependent variable, which is uniquely explained by an independent variable. So it's a similar structure to what you were thinking with the Pearson's correlation coefficient. You have Pearson's R, and then if you have two variables, then like an independent variable and dependent variable, if you square that, you get your coefficient of determination, the amount of variance accounted for. In the same way, with semi-partial correlations, you have SR, and if you square it, you get SR squared, which is the amount of shared variance between the variables. So the semi-partial correlation squared indicates percentage variance that's uniquely explained. So that's the key thing here. So before, I was saying how there's a situation in which the semi-partial correlation may be equal to the correlation. And so here is in this first Venn diagram on the right here, here's an example for where in both these scenarios, you can see there's no shared variance between independent variable 1 and independent variable 2. So because there's no shared variance, the semi-partial correlation will equal the correlation, right? However, in this example, there's this shared variance here, similar to what we saw in the previous example. So in this example, this is where we'll see the semi-partial correlation will be less than the correlation coefficient. And so we can compare each SR squared with the R squared or SR with the R. And if they differ, think about why this might be the case. If it stays the same, there may be no overlap between the predictors. If it drops substantially, there's possibly a strong relationship between predictors. And so really the SR squared key thing to take away is that it's about the unique variance. And then you can compare that with R squared. If they're equal, you know those variables are in this category here in the first diagram where they don't have any shared variance with one another, right? So that there's no shared variance, it's all the same. So the semi-partial and normal correlation coefficient are the same. But if there is shared variance, the semi-partial is just the unique variance for that independent variable. So it's going to be smaller than the R squared. So let me give you an example to emphasize this even further. So are individuals more likely to have poorer brain health when they have higher cardiometabolic risk? So hypertension, obesity, for example, or dyslipidemia, which is changes in lipids, or when they experience menopause-related changes, for example, the hormonal transition. So how much of the changes in brain health are attributable to cardiometabolic risk compared with menopause, compared with the shared between the two. So how do cardiometabolic risk and menopause relate to brain health outcomes? For example, cognitive performance or dementia risk. You can take any sort of measure there, but really conceptually, I want you to see that there are these two measures and we're looking at their relationship with some brain health outcome here. So this is all fictitious data. I just put it together to give you an example of what this concept is really demonstrating. So the semi-partial correlation here indicate the relative importance of each predictor, right? So here we see it's 0.39, and for menopause it's 0.1, and the cardiometabolic risk it's 0.51 for Pearson's correlation, and menopause is 0.35. Already what should be pointing out to you is that you can see the drop between the zero order correlation and the semi-partial correlation. So that should say to you that there's some degree of shared variance between these variables that's there, right? Because, and we can square the semi-partial correlation and get the percentage of variance uniquely explained by each predictor. So I've done this for you. So the R squared indicated, so this is our usual coefficient of determination, just looking at the shared variance, nothing unique, just the shared variance between our independent variables and our dependent variable. It indicated that cardiometabolic risk and menopause explain 27.3% of the variance in brain health outcomes, right? So that shared variance is between all the measures is 27.3. Squaring the semi-partial correlations that are here tells us how much unique variance each independent variable explains. So cardiometabolic risk, its semi-partial correlation was 0.391, and squared it's equal to 0.153, so it's 15.3% of the variance. And for menopause, its semi-partial correlation is 0.109, squared is 0.012, so its unique variance through the semi-partial correlation is the 1.2% of the variance. So to explain the variance in brain health, you sum the semi-partial correlation squared, so that's 1.2 plus 15.3. So 16.5% is uniquely explained by the independent variables, and R squared, with minus the sum of SR squared, so the R squared representing the shared variance, and then the sum of SR squared representing the unique variance, you get 27.3 minus 16.5. So that allows you to know that 10.8% is explained by the combination of the independent variables. So for example, shared variance. If you didn't get that, don't worry. Here is a diagram to show it a bit further, right? So here are our variables, just like we had before. We have cardiometabolic risk, menopause, and brain health. And we see that they're unique. This is not the greatest Venn diagram by me because you can see these are not proportional to the size. But in any case, conceptually, it maps on. So cardiometabolic risk is 15.3% here. Menopause is 1.2%. So that's the unique variance that they have. And the shared variance here is 10.8%. Right, so not to scale, but it's all there. And so that's how you can see in total that when you look at R squared, this is R squared, right? All of this is R squared. How much of the variance in the dependent variables accounted for by your independent variable measures, right? So we get that 27.3%. The SR squared is our unique variance for each of these measures. Yeah, and that's semi-partial correlations in a nutshell. It's just about unique variance, and you can see how it can be useful if you want to get a sense as to, okay, these are all the predictors that I have, but what about individual predictors? What are their individual contributions? So in summary, in multiple linear regression, partial correlations are represented as SR, and you square the SR values to obtain SR squared, which is the unique percentage of dependent variable variance explained by each independent variable. We can then discuss the extent to which the explained variance in the dependent variable is due to unique or shared contributions of the independent variables. So it's all about variance, right? We're interested in how much of it is shared, how much of it is unique, and you get a sense of the contribution of individual variables to the overall dependent variable. So what do you need to do? You need to be able to understand conceptually what semi-partial correlations are telling you, but you don't need to be able to run these. That's not an expectation of this course. Really, it's just the theory of understanding what a semi-partial correlation is and what they're telling you when you see the semi-partial correlations. Excellent. So in saying that, I think that's a good space for a break. Stretch your legs, grab a tea, and we'll get started with the next section.